That's great. Thanks, Greg. I want to do quickly just before that, I want to step back into the teleop code for a moment and just make a couple important points. And these are common stumbling blocks that teams often face. Without going into too much detail, we've already given a tour of this code. Just want to give an important caveat. Be very careful not to create any custom code inside this loop, which takes any time to execute. In other words, let's say we wanted an action which was to open a gripper, wait a couple seconds, and then close the gripper. We have to be very careful not to implement that inside one of these structures. If we did that, then what that's going to have the effect of doing is slowing down an entire loop so that we don't read our next packet for several seconds, which is a very common cause of a completely non-responsive robot, which can be dangerous to the robot and also certainly not be effective to your gaming strategies. So that's one point I want to make, and the way that we achieve that, and Greg already hinted at that behavior, one of the ways that we can achieve that kind of behavior is with the advanced sub-VI. And in the final webinar in this series, we're going to go into a lot more detail about some of these advanced tips and tricks where we can achieve some of the more custom functionality that we might need to have a really successful gaming strategy. So let's jump back now. I'm going to go ahead and close my teleop program. Also close the remote control editor and jump back into our autonomous mode code. This is very similar code to one which we've described in previous webinars. And what I wanted to do quickly was give a tour of this code, reminding and explaining as we go of the behavior, how it works, and why it's done that way. But before we do that, let's take a look in context of what our goal is for this autonomous code. In general, autonomous coding should take a lot more time than the teleop coding because the autonomous code is not created for you. Unfortunately, there is no generate autonomous code function built into this because, of course, everyone's behavior, everyone's robot is different. But there's a really great way to get started. The Tetrix Getting Started guide material, which we've previously referenced in other webinars, is a nice way to get started and building on, because a standard robot with an arm and a gripper and a couple DC motors is a very common building block for a successful FTC bot. So the code that we're going to look at today is following the flowchart that you see on the screen here. It's a simplified version of something that we've done in previous webinars. Basically, it's going to just drive looking for a target. When it finds a target, it's going to actuate its arm and its gripper to grab it and pick it up. Okay, so let's look at this through the flowchart context. So if we start here, we say, well, we're searching for a target. And we're going to define a target as being found if there's something within 17 centimeters as determined by our ultrasonic distance sensor. So if nothing was found, then we're going to just drive straight. As mentioned, this was similar to a previous example, but in that case, we were doing a line follower instead of just driving straight. So this is a somewhat simpler example and probably in general more applicable to the FTC context. So when we're driving straight, we're going to make a decision on how fast we go based on whether or not we see something within 30 centimeters. So there's nothing really close, but if there's something kind of close, if there's something within 30 centimeters, then we want to go at a speed of 15. If there's nothing within 30 centimeters, nothing in view, we're going to go faster so we can get there in a hurry. So this top part of the flowchart is making the decisions about how fast we drive, basically. And then the second part of the flowchart is, well, what happens when we do find a target? So if something is found within 17 centimeters, we're going to lower our arm, close our gripper, and then raise our arm. And we're going to do a quick check with the touch sensor to determine whether or not we actually pick the thing up. And so there's two end results here, whether or not it emits a sound saying success or whether it writes a failure status to the NXT screen. So that's the goal of this code. Stepping back now into the block diagram of this code, I'm not going to create it from scratch. We've done a bit of that, and as a bit of a sneak preview, several of the next upcoming webinars are going to be giving a lot more detail about creating code. So we're going to just give a tour of this code so that we understand all the pieces. And so it's a great way to get going and make the modifications yourself. So we've got the same initial loops that we had and we talked about in the last webinar, which was communicating with the field controller software, determining the robot state, and basically waiting for everything to be ready to go. And once it is ready to go, then this loop finishes, which allows us, because of the paradigm of data flow, to get into and start executing what's inside this sequence structure. And this is, when you open a blank template, basically where the autonomous code goes here. So we're going to be communicating with both our servo and our left and right drive wheels. So we've got a pair of constants out front here. It's great practice to leave these constants outside. And we've talked about that in a previous webinar as well, because you can wire them up into several functions. You don't have to have copies of these constants all over the place, which serves two purposes. One, the code is cleaner, and two, if you ever changed the name or needed to change which gripper, or which servo or motor you're talking to, you've only got to do it in a couple places. You don't have to do it all over your code. So the first thing we do, and we're following our NXT terminal in and out of all these functions to determine the sequence. First thing we're going to do is initialize our positions to be 255 and 0. Bring back our handy dandy context help just so we know which function is which. So we're moving our servos to 255 and 0, and then we're waiting for 1 second. Next, we're going inside a loop. And the first thing this loop is doing is checking the reading from the ultrasonic sonar detector. And it's reading a value out of port 2, and it's giving back a number. It's looking at that number and doing a comparison to the value of 17. So remember, if it's closer than 17, that's when we're going to go and perform our gripper actions. So if we're closer than 17, we're in the true case. We're going to stop our motors. We're going to stop our way out of this while loop, and we're going to carry on. Whenever it's in the false case, then we're going to do our speed check. So if the distance is less than 30, great, we go speed of 15. If not, we go a speed of 30. So this is that upper branch of our flowchart that we were just looking at. So assuming that we've found our object, we get out of this while loop. We're now into this portion here where we're making some commands to our servos individually. So this is why we've got separate constants for the arm and the gripper. Because remember, whenever we do a command to a move servos or a DC move motors, we can have multiple constants wired up here. If it's just one, we get just one input. So we've elected, because we want to command our arm and gripper separately, to do separate single DC move motor commands. Move servos commands, sorry. So the first thing we're going to do is move the arm to a position of 255. Then we're going to wait 1 second. And then, following this constant up here, we're going to move the gripper to a position of 0. Then wait 1 second. Then we're going to move our arm to a position of 0. Wait 1 second. And finally, we're going to check that touch sensor by doing a sensor read with the touch sensor selected from the polymorphic selector terminal, and then making a decision based on that which state of this case structure will run. So if the touch sensor is pressed, we're displaying text, success, and beeping. And if it's not, we're saying failed. So this code, or something much like it, is probably going to be the kind, or at least the similar to the form that most teams' autonomous codes are going to look like. There's going to be some combination of servo and DC move motor commands. There's going to be some comparison functions. There's going to be some point where you're within a while loop waiting for something to be true or false. There's going to be some point once you get out of that while loop where you're going to be making and performing another action. You're going to be reading from sensors in order to make decisions. And you're going to probably have code that's very similar to this that may or may not have an outer while loop and may or may not be doing something like line following. And so our goal in this part of this webinar was to give you an explanation of these basic building blocks, and hopefully that you'll understand within the context of what your robot needs to do, how you can extend, manipulate, and modify this kind of example to really have a great strategy in your FTC game this season. So at this point, I'd like to open up the question and answer portion. Please feel free to ask any questions at this time, and we'll be happy to illuminate as best we can. Okay, I see a question from Jason here. The question is, what's the best way to get your FTC robot to switch from autonomous to teleop during the game? We had issues with that last year. We were not sure on how to properly achieve that. Our robot would not switch to teleop when it was time.
That should be automatically handled through the FCS for the most part. We may be talking about the program chooser later. Through the program chooser, you select your teleop code, I believe, yes. You deploy your autonomous before you give it the go-ahead from the FCS. And then once you hit go on the FCS, after the autonomous period is up, then it should automatically switch to your predetermined teleop code.
And I think it's important to note, Jason, that you can test that out yourself with the FCS outside of the context of competition to make sure it's good. Can I ask a follow-up question, Jason? Was your coding done in LabVIEW last year? The answer is yes. This may be a situation, just thinking out loud here, perhaps if you do make changes to the teleop or the autonomous code outside of the template where you should make changes, you could, in theory, alter the behavior of the code. So without taking a specific look at your code directly, I would just add the general caveat to make sure that you're not placing code outside of where it's supposed to be.
And one thing worth note is in the FCS, after you've connected to your Samantha module, if you hit details on your Samantha module, there should be a little section that says teleop program, and before you even hit anything, it should say the name of the VI that is going to be deployed once you start it. So make sure that correct VI is showing up there in the details section. And again, you choose that, I believe, through the program chooser.
Second question from Jason: is there a way to see a copy of this webinar online? Absolutely. Within as soon as possible, which is between a couple days and a week, this will be posted on tetrixrobotics.com/FTC. And in fact, the previous 3 webinar videos are there right now for your viewing pleasure. That's tetrixrobotics.com/FTC. All right, well, thank you very much for joining us. In this fourth in our webinar series, we talked about how to generate, modify, and test the teleop code. We talked about the autonomous code template and did a pretty detailed look at one particular example. So please take some time now to register for the next webinar. Look forward to talking to you again.